Hello, my name is Jordan Ruffner, and I did my ME541 Project 2 on quantum models of cognition and decision making. I chose this topic because of my interest in quantum mechanics, and I was curious to see how it applied to the cognitive science realm. The sources that I used for this presentation, I used a total of 3 sources, 2 articles, and one book. The 2 articles, one of them, Quantum Cognition, A New Theoretical Approach to Psychology, was released in Trends in Cognitive Sciences, Volume 19, and that was written by Peter Brusa. And I also used Quantum Cognition, which was an annual review of psychology, Volume 73, written by Jerome R. Bussmeyer and Emmanuel Pothos. The book that I used, Quantum Models of Cognition and Decision, I gained a lot of information from and read through quite a few chapters of that. It was written by Peter David Bruce and Jerome R. Bussmeyer. I'd like to point out that Jerome Bussmeyer was a prevalent uh, prevalent author in a lot of these articles. He was either the primary author or referenced in them. He seems to be a renowned researcher in the topic, and I used this research to gain or his research to gain my knowledge in quantum theory cognition, and the rest of this presentation is based on the knowledge I gained from these sources. An outline for this presentation: I'll give a brief background on the history of quantum theory and then why we use quantum theory in cognitive sciences today, basic principles of cognitive quantum theory, and how quantum theory compares to traditional models and why it may be advantageous to use, and then a hypothetical example applying quantum theory. So, a history on quantum theory. Underlying classical probability theory is a traditional theory that was used before quantum theory, and it's prescribed by Boolean algebra because of its set theoretic foundation. This implies that events can always be combined. That is, if you have event A and B, that would be equal to event B and A, regardless of order and regardless of outcome. Now, realistically, that is not always the case. So, quantum theory was axiomatized by John von Neumann in the early 20th century, and it's a branch of quantum mechanics, but it's not a physical theory. It does not suggest that the brain is a quantum computer, but it rather uses the mathematical structure of quantum mechanics and its associated dynamic principles to analyze decision making on a dynamic scale instead of a definite scale. That is how classical probability theory analyzes decisions. And rational models of cognition adhere to the laws of classical probability, where human reasoning does not always conform. So what is quantum theory? Quantum theory is a generalized theory of probability, just as classical probability is. We'll be using classical probability as a sort of basis for this presentation because quantum theory was axiomatized from classical probabilities. Some of the axioms are similar, and some even say that quantum theory is a more generalized and less restrictive theory than classical probability. So quantum theory measures non-commutativity, where traditional models measure commutativity. That is, where if you have event A and an event B, the outcome of event A will not influence the outcome of event B, and realistically that is not the case. So non-commutativity would be the instance in which the outcome of A would affect the outcome of event B, and in the order in which they appear or occur affects one another. So this brings back complementarity, where you cannot measure events or something simultaneously, but both the measurements are required in different reference frames. So we'll go over different perspectives and how quantum theory utilizes different perspectives to measure certain order effects. Quantum theory also uses a vector space, where traditional probability theories may not, which we'll go over in the next slide, and it represents dynamic models multidimensionally, and this is beneficial for neural network models that prefer vector spaces for thought processes. So the basic principles of quantum theory: compatibility. like we mentioned on the previous slide, complementary, where some questions are incompatible and that cannot be considered simultaneously. So compatibility introduces incompatible events. So A and B would be incompatible if the outcomes of one another influence each other. So different perspectives are required to analyze how event A would affect, how the outcome of event A would affect event B. Another basic principle of quantum theory is superposition, and this can also be related to quantum mechanics, where superposition is a state in the universe where all possible definite states have potential for being actualized. So just as a particle in quantum mechanics is not, its exact location is not actualized in space and time until you measure it, that is the same for quantum theory and cognition. So a decision maker can be in between two alternatives, and at any instant that they are measured or asked a question is only when you can measure their probability. So other basic principles: interference, entanglement, and order effects. The outcome of one event can inadvertently affect the separate event. That's interference and entanglement, where information in space and time can affect another event. And order effects, where the order in which you ask questions or events happen will dictate the outcomes. So quantum theory versus traditional models. Quantum theory, each outcome is a vector in a vector space, where classical probability, each outcome is a member of a set of points in a sample space. So we're dealing with a vector space instead of a sample space. So multi-dimensional in the vector space. And each event in a subspace is a subspace of a vector space for quantum theory, where each event is a subset of the sample space in classical probability. So the probability in quantum theory is defined by the squared length of the unit vector in the vector space, and the probability defined in classical probability is defined by subsets. And each of them work on non-commutative and commutative characteristics, as we described earlier. So to give an example on quantum theory and to apply it, we'll use the Linda problem. So the Linda problem is a common example that shows the conjunction fallacy in traditional probability theory. So in the experiment, participants were asked about a certain individual, Linda, and what alternative would be more probable. One, Linda is a bank teller, or two, Linda is a bank teller and is active in the feminist movement. So on the right hand side is the vector space, and I will point to the axis, the feminist axis, in which she is indeed a feminist, is this horizontal blue axis, and the vertical axis would be she is not a feminist. And on the red axis, you have she is a bank teller, and then she is not a bank teller. So the pink vector is a unit vector in space and time that the decision maker is between each alternative. So it is not until it is measured that you can determine the probability. And the measurement can be in the form of asking a question. So say Linda is a bank teller. That's the first question you ask. So you would go from the unit vector down to the axis of the bank teller, which is the red reference frame. And the probability would be the squared length of that unit vector, which gives you a probability on this line. Now say that the question was asked on the feminist perspective first. So is Linda a feminist and a bank teller? So you would be answering the question from the feminist perspective. So first you would go down to the feminist axis and then down to the bank teller axis, and that squared value is the probability. And as you can see between the blue and black lines, the probability varies. So this is an example of a conjunctive fallacy, where the probability of conjunctive events can never exceed the probability of one of its constituent events. So that is, Linda being a bank teller cannot, or Linda being a bank teller and an active feminist cannot exceed the probability of Linda being a bank teller. because Linda being a bank teller is also included in the second alternative. So this is just an example of how quantum theory would use different perspectives to find the probability of an alternative. So in summary, the new approach, quantum theory, can model dynamic systems. Dynamic systems are preferred for incompatible events that impose sequential evaluation. They provide an effective solution to bounded events, but they do raise the question of rationality. Classical probability theory may provide an upper bound that achieves optimal performance, while quantum models may provide a more realistic bound that performs close to optimal. So quantum theory does not necessarily discredit or disprove traditional theories, but instead it expands on them and allows a more realistic approach from traditional decision-making methods. Before I conclude this presentation, I want to give an example of where I think quantum theory would apply in an everyday situation. So at the voting stand, I believe that quantum theory applies where you would be asked, say, if one candidate serves climate change, better than the other, or how well they serve climate change. That could affect your decision on the other candidate if you have strong opinions on climate change. Whether or not the other candidate has other attributes that are well off, it may be the preferred candidate. You were biased by the questions that you asked. So sequential ordering and the superposition of your beliefs dictate how you would answer that question. So I found this project to be very insightful, to be able to look at another topic that we weren't able to discuss in class, but be able to apply topics that were discussed in class, like classical probability theory, and incorporate those in a more complex topic, and also a topic that relates to personal interests of mine, like quantum mechanics. So I appreciate this project, and I think it was very insightful.